Our first full-length talk of this session is a collaboration between 3 different companies. We have credited speakers from Mellanox, Red Hat, and Nuage Networks from Nokia. It looks like our first speaker is Anita. Is Mark from Nuage. So come on up.
Yeah, thanks. Right slide here for the start. Clicker going. And so there's Maj here from Mellanox and also Anita from Red Hat. So I'll start off with a few introductory remarks. So the title of our presentation here is The Long Road. I don't even remember, it's so long. The Long Road to Deployable OvS Hardware Offloading for 5G Telco Clouds, which is quite a bit. And we put the long road in parentheses to really underscore that that's a retrospective thing. That's the past. So what we're really wanting to do here is kind of recount some of the past 3 years or so of evolution that's happened in terms of bringing OvS hardware offloading to maturity and for relevance in the context of a 5G telco cloud. So please mind the brackets there, please. We don't want you to walk away with the impression that somehow this is all work that has to happen in the future. Most of this is stuff that's been accomplished, but we will provide some forward-looking comments towards the end. So to kind of get this rolling, I fished out a diagram I saw way back in like 2016 that talked about this concept of OvS hardware offloading. And the idea is that like you would have a packet come in, and the first time it came in, it would get processed either in user space or in the kernel, and then eventually whatever you found there in the kernel could actually be replicated or programmed into the NIC itself, and then do processing. And the kind of performance levels you could see there were pretty soon validated to be like substantially higher than what you might normally expect to see on a generic processor going through the Linux kernel, at least. Maybe not with DPDK, but at any rate, there seemed to be a tremendous opportunity there to get much better performance, and that really relates to using a tool that's really right for the job. So the idea is that if you have an ASIC that's custom designed to do certain operations, it might be very efficient at doing these things, and therefore you could get much better performance if you have a standardized way to leverage those and a uniform way to take advantage of those kind of functionalities. And so really this whole talk is about the evolution of that from the time of 2016 onwards up to the point today where it's ready for deployment. And I put in a bunch of logos here, which I actually stole from Anita. She had put these together in the past, I think. But to make all this stuff work, and this is along the lines of what Rashid was talking about earlier too, where you get rid of the command line. There are many different projects involved in making all this stuff play together. So there's a lot of moving parts. And while you can put this together and make it work fairly simply, to get everything to play together is no small undertaking. So with that, I'll just roughly outline some typical requirements for the telco cloud. And these are certainly not only found in the telco cloud. I'm sure many of these kind of characteristics are found even in private data centers and other places, but first of all, virtual networking is sort of fundamental. To achieve the economic benefits of virtualized computing, you need to have an ability to separate tenants that are operating on your network, and typically that's done through VXLAN encapsulations or some form of encapsulation. And then you'll find an enormous amount of redundancy built in to the networks that are deployed for telco clouds in order to get resiliency, because staying up and running is all important. Downtimes are not just lost revenue, they're lost reputation, and so that's a serious issue for most telco service providers. And then beyond that, there's to support that, things like bonded uplinks, support for LACP. You have VLANs from the VNFs, so you have VLAN trunking going on. You have route discovery. If you have distributed controllers, for instance, you may have to do BGP route discovery to exchange routes. Support for things like mirroring, You would like to be able to offload those things to increase the performance of your system while at the same time doing some very heavy-duty lifting in terms of pushing packets around. Performance is also very important in the telco cloud, particularly where you have a lot of messaging going on or different protocols you have to deal with. You're dealing a lot with small packets at very high rates, and you want to maintain low latency and keep things operating in order. And then finally, flow creation and eviction and churn, all these things are very critical to the efficient operation of a telco cloud deployment. And then there's scale, there's cost, and certainly OpenStack or Kubernetes integration. There has to be some orchestration, so the whole thing is part of a much bigger picture. So I have two diagrams here that highlight some of this. In this diagram, we're really highlighting the redundancy of the networks. So you can see here on the left, for instance, a stack that includes both the host network stack and then also the guest stack. And what you see here also are like redundant TORs, and then the TORs become part of a leaf spine architecture. So you have lag operating there, and then if you have a lot of VFs on each one of your hosts, we introduce what's called VF lag, and we'll talk about how that's supported later on. And then these things may be geo-distributed, so there may be a cloud interconnect between these different deployments. And then beyond that, if we look at the traffic itself, there's this notion of north-south. So typically north-south is user traffic coming into the overlay, and then east-west is traffic that's moving or transiting over the overlay between different VNFs. So for instance, you may have service chaining going on between certain VNFs as packets have come in and they're being inspected or processed or whatever has to happen to them depending on what the function is there. So these kind of architectures present great challenges in terms of making everything work. Sometimes you have to deal with things like tagged packets. So I've labeled some of the interfaces here to the VMs as either tagged or untagged. And if you think about all the different possible combinations of tagged, untagged, local to remote, so on, it gets pretty complicated to make sure every one of those cases can offload. So there is a fair amount of complexity going from just a basic, this thing can offload, to like it offloads for every possible case that you can think of. So with that, we sort of set the stage here, and I'll turn it over to Anita Majd, to go a little deeper into a lot of the work that Mellanox has done in terms of making this happen.
Thanks, Mark. Okay, so my name is Majd, and I'm going to elaborate a little bit more about the features that we had to offload to the hardware in order to meet the telco cloud design. So we'll start with the bonding offload, or VF lag. So basically now that everything is offloaded to the hardware and we are using SROV, all the traffic is transmitted directly from the VFs that reside inside the VM to the hardware. So basically we bypass the Linux bond and we lose all the functionality that we had before. So in order to preserve it, what we actually need to do is mainly two things. We have the link aggregation. So it's the ability of aggregating two physical ports into one, a logical one, and then the application can see only one logical port and utilize it. The second requirement would be high availability. So it's something that Mark also mentioned that is very important for resiliency, that we will have high availability, that in case of one of the links fails, then we can do a failover to the active one. So these are the main functionality of the bond device, the Linux bond device that we had to offload in the hardware. So what would be the expectation? So it's actually, once we have a VF, we would like to aggregate both of the physical ports, the two physical ports, and every VF can transmit and receive data on the two physical ports without any issues. Second thing would be transparency to the VM. So this is also another requirement that, or expectation, that the VM does not have to do anything special and can enjoy transparently this functionality of link aggregation and high availability. And as for user experience, we also would expect it to work the same way as before. It's just by probing some bond device, enslaving the two physical ports of the NIC, and enjoy this functionality. So how we actually do it with hardware offload, so it's composed actually of two parts. There's the first part of the resiliency. So in order to enjoy resiliency, we need to duplicate all the rules in the RX to both embedded switches. So when we are working with two physical ports, it's important that the same flows will be on the two embedded switches. So we do so in two ways. When we work on the uplink representers or the bond device, we utilize the infrastructure of shared TC block. And this way, each rule that is added on top of the shared TC block will be replicated to the two uplink representers. And this way, we can make sure that both embedded switches are in sync. And in case one is going down, the traffic will continue to be transmitted to the VF with all the correct actions. The second thing would be the representers, which actually the representation of the VFs on the open vSwitch. So in this case, since we can't utilize the shared TC block, what we actually do is replicating all the rules in the hardware, and this way we can achieve the high availability. The second thing, in order to achieve the high availability, the second thing that we do in order to complete the high availability is listening to all the NetDev events inside the driver to get notification which link is actually active, and in case one of them is inactive, then we notify the hardware which one is inactive and which one is active, and this way the hardware will know how to transmit the data on which port. And in case one of the links that was inactive is active again, then we need to notify it again. So with these two things combined, we can achieve the same high availability that we had in the Linux bond. In order to have the link aggregation on the TX side, what we actually need to do is distribute all the send queues of the VFs on the two different physical ports. So this is something that we do in our firmware. So the firmware is responsible to distribute the SQs to the two different ports, and this way the VM can utilize both ports transparently by seeing only one. Another interesting thing is all VLAN tagging. So as Mark showed in his diagram, we have a lot of tagging. We have traffic coming from the VNF that is tagged. Some of it is not tagged. We have tagging on the overlay, tagging on the underlay. So in order to preserve the same functionality as we had without hardware offloads, we need to support all of them. So we can look at it as two major groups, the overlay tagging and the underlay tagging. So for the overlay tagging, we need to have the ability to push VLANs, and then, for example, do an encapsulation, or the other way around is to pop VLAN and replace it with a VXLAN encapsulation. So this is these functionalities were added in hardware offload in order to preserve the same thing that we had before with the software solution. In addition, we have the underlay tagging. So for the underlay tagging, it's mainly used for segregation between different types of traffic, and this is also something that we can support, is adding the tag on the underlay on the outer header in order to get this type of segregation. Another thing is the header rewrites that we need to support as well. For example, for routing and other things, load balancing and all the other techniques. So we do support TTL decrement. That is very important for routing across subnets, that each time the packet traverses across subnets, we need to decrement the TTL in the hardware in order to preserve correct functionality. Another thing is the TOS, that we can replicate it or inherit it from the inner to the outer headers, and in this way we can preserve the quality of service. And another thing that we can do as well is the UDP source code that can be a calculation of a hash on the inner packet, and this way we can provide an entropy to the ECMP. So all of these things are very important to preserve the same design that we had before in the software solution once we move to a hardware offload solution. Another interesting feature that is very important to the telco market is remote mirroring. So remote mirroring is actually duplicating the traffic of one VF to a remote node. It can be a VF or a host. So this is also one of the most important features, I guess. It's a very interesting feature because it's needed also for debuggability, monitoring all the important stuff that people talked about here once we work with hardware offload. So debuggability and monitoring are very important. And also for telco market, we have the low-fall intercepts that we must have this capability, otherwise the solution is not a valid solution. So for remote mirroring, we have many use cases, many different use cases that we do support. For example, in this diagram, we can see that we are transmitting data to a remote VM, like we are remote mirroring a local traffic from one VM to another VM to a remote VM. So all the traffic that is being transmitted from VM 11 to VM 12 will be transmitted to a remote destination, VM 21 in this case, over a VXLAN tunnel. Another case where both traffic are remote traffic, so traffic transmitted from VM 11 in this case to VM 81. Yeah, VM 81, no, sorry, 22, over a VXLAN tunnel. Then we need also to be able to replicate this traffic over a VXLAN tunnel. So this is also something that we have added and support in the hardware offload. And another interesting case, it's the other way around, where the traffic is replicated actually on the host of VM 11. So all the traffic that is received on VM 11, we can first of all decap it and forward it to VM 11. And on the other hand, we can replicate it, put it on a GRE tunnel, and remote mirror it to another host. So here's an example of the data path rule that actually shows that this kind of a complex rule, very complex rule, is offloaded in the hardware. We can see that the traffic is received on one of the hosts. It goes through decap and transmitted to the VF, and it goes also encapsulation of GRE tunnel and transmitted to the GRE tunnel. So that would be all for the interesting features that we had to cover in hardware offloads in order to meet most of the use cases of the telco market. And now I'll let Anita continue with the future steps.
Thanks much. We're looking ahead now, and here's what we would like to do in the future, as well as look at community collaboration in some of these areas. So we have a list here of all the features that we do support currently, and that makes the solution today deployable on telcos. But we're also looking at work in progress items, and some of them we've already discussed. We have a goal to increase our flow insertion rate with TC parallelization and software steering, and traffic engineering with MPLS segment routing, load balancing firewalls with connection tracking that was already covered, and VDPA to support replace SRIOV and live migration support. Now let's look at flow aggregation and what that implies. Today, we need to worry about whether flows are static or dynamic. When OpenStack deploys a VM, all the mega flows and VXLAN aggregation are dumped onto the OVS vSwitch. And then when we get the first packet come in for the microflow or the user flows, the mega flow is offloaded to the NIC. And we assume that all future expansion to microflows is going to happen on the NIC. But that's not the case. There are cases where we need to worry about looking at the inner headers and the user flows and be able to do dynamic flow churn and handling dynamic flows. Here are some examples of where dynamic flows are crucial. Routed flows. When we are doing routed flows and you're going from one subnet to another, then you need to decrement your TTL. And the decrement TTL, and you can see that there are a lot of routed flows in the overlay VXLAN solution. Anything that's north-south, any east-west between tenants, and remote mirroring is all routed flows. And TTL decrement today is in the kernel is done as a match and a set. So you're going to match every single TTL of a flow coming in and then set it. And there's a patch that we're working on to do it the right way and offload it to the NIC. And then if you look at entropy and ECMP support across 4 paths, ECMP paths, where we are setting the UDP source port based on the inner L2, L3, and L4 headers. We're using DP hash, and we have an issue today with DP hash where the first packet done by vSwitchd does not match what the kernel and NIC DP hash value is, and so we have to do this in user space today, and that means there's a flow explosion in the user space, and we can't offload it right now to the NIC. But there's work in progress to solve that as well. And on a future, looking into the future, we would like to do services like load balancing between services in a service mesh kind of use case. And this could be with Kubernetes or OpenStack, where user flows need to go from one VNF to another. And the remote VNF is a set of redundant VNFs addressed by a virtual IP. And so OVS would need to look at that virtual IP and expand it into 3 VMs or VNFs that are the destination, potential destination, based on the number of user flows coming in. We would also like to do network policy and firewalls with ACL, either stateless or with connection tracking. And this implies like VM1 cannot talk to any other VMs except VM3, and VM2 and VM4 can only talk to each other. And we need to implement these kind of firewall use cases either with stateless or connection tracking. Mellanox has a bunch of connection tracking patches that we would like the community to look at and review. And because we have this flow explosion possibility with all the future use cases, we would like to increase our flow insertion rate to go beyond 10K flows per second. And there is work in progress both in the kernel and on the NIC drivers upstream to add TC parallelization and to bypass the RTNL lock, as well as work on the driver side for software steering patches. Looking even more further at MPLS support with MPLS UDP and segment routing for edge use cases. And today, everything is done with VXLAN overlay tunnels. And VXLAN requires translation. When you're going from one data center site to another, the DC gateway has to translate your VXLAN tunnel into an SD-WAN MPLS VPN. And the goal is for edge sites to be able to bring that MPLS all the way down to the host at the edge, and to be able to do L3 BGP VPNs or VPLS from your spine and your spine routers end to end, and have a global SDN controller that talks to the local ones, and to have segment routing MPLS within the data center, sharing labels over OSPF and ISIS, and to build a multi-label stack. The eventual goal is traffic engineering. With VXLAN, we're not able to get as much control on the data path that we would like, and the customers are asking for being able to do source-based policy routing to pick paths within the network, depending on the time of day, depending on the type of service, to pick specific paths going over the network and going end-to-end from edge to core or back. And here's just, I will not go into all the details on this, but this is the different types of encapsulations that we're looking at. You can have a data center with segment routing MPLS, data center with MPLS over UDP. MPLS over UDP solution is preferred in cases where you may have in your data center switches that don't support native MPLS, and you need to use UDP for your entropy, and then VPN MPLS labels on top. We want to be able to support both L3 VPN with IP encap, as well as VPLS with layer 2 Ethernet encaps, being able to ship between data centers. And here is what we're expecting from the OVS and kernel to support both these use cases for MPLS over UDP and segment routing. There's work on the OVS side as well as kernel side, and work in progress and patches upstream that are being discussed, as well as MPLS over UDP support and NIC offload support.
All right, we're almost out of time here, so I don't think we have time for a question, but thank you to all of our speakers from Red Hat and Mellanox and Nuage.